Good day, everyone. How are you doing today? All right, welcome to today's tutorials video by the National Fellowship of Christian Pharmacy Students, NFCPS for short, UNN chapter. So today we are going to be doing a tutorial on adsorption experiment. And right standing before you is a 400 level pharmacy student, as at this time when this video was being recorded, Ede David Chibuzo. So we're going to be talking about the adsorption experiment, and I'm going to be explaining to you some of the hacks that will help you to do very well in your adsorption practical, both the normal practical and the practical which you have as your examination question. So what exactly is adsorption? Adsorption simply refers to the process whereby a material or a substance or a chemical species, which is usually referred to as an adsorbate, adheres to the surface or the interface of another substance, which we also refer to as adsorbent. So when we have a chemical species or a substance adhering to the surface of another substance or the interface between itself and another substance, then what we have there is a process called adsorption. Adsorption is different from absorption. Absorption goes inside, adsorption remains at the surface. So, and there are different kind of adsorption we have. We have the chemical adsorption, which we call chemisorption. We have the physical adsorption, which we call physiosorption. So you have to go in details and check out your materials for you to be able to get that aspect of adsorption. So, but for today's video, what we are going to be focusing on is the practical of adsorption, the practical experiment on adsorption. So adsorption usually has different theories or different equations that can be used to explain it. So, but for today's video and for the purpose of this particular course, we're going to be looking at adsorption from the standpoint of the Freundlich equation. From the Freundlich equation, and that equation is x over m equal to ky raised to the power of n. Ky raised to the power of n. So these are the things we have in the Freundlich equation that explains adsorption, appropriately. So let us look at the meaning of these particular terms we have here. Now, the x simply refers to the weight. The x simply refers to the weight of the adsorbed substance. The weight of the adsorbed substance. And then our m simply refers to the mass of the adsorbing substance. And then our y, let's work with the y, please. Now, the y we have here, our y is actually the concentration of the adsorbed substance, at equilibrium. The weight of the adsorbed substance at equilibrium, and then our k and n are constants as the given condition in which the experiment is being carried out. Now, for this particular experiment, we're going to be looking at the adsorption process of acetic acid, which is the adsorbate, on charcoal, which is the adsorbent. So we are going to be working with in adsorption we have the adsorbate and we have the adsorbent. So for today's practical video tutorial, we are going to be working with the adsorbate as acetic acid, and we're going to be having the adsorbent as charcoal. So in the context of this particular equation, the weight of the adsorbed substance, which is the adsorbate, it means that what we're talking about for the x is the weight of acetic acid, since this is the adsorbed substance. And then the mass of adsorbing substance, which we refer to as the adsorbent, it simply means that what we're talking about here is the charcoal. And then we say concentration of the adsorbed substance, that means we're talking about the acetic acid in this particular concept. And then the k and the n are constants at any given condition. So if we do a log equation of this particular equation, we'll have something like this. We'll have log x over m, we have log x over m is equal to n log y plus log k. That's when you do the logarithm of this Freundlich equation, we have log x over m equal to n log y plus log k. Now, this particular equation can be likened to the equation of a straight line graph, which we already know to be y equal to mx plus c. This is the equation of a straight line graph. This is on the y-axis, this is on the x-axis, and m represents the slope and c represents the intercept on the y-axis. Now, if we want to compare this equation to that of a straight line, it simply means that the x over m, the log x over m is like something that can be on the y-axis. You can plot it on the y-axis. Then the log y can be plotted on the x-axis. The implication is that when you have log x over m on y-axis being plotted and log y on the x-axis being plotted, when you get your slope automatically is going to give you your n, which is a constant. And then c is the intercept on the y-axis. So it means that if you plot a graph of this against this, your intercept is going to give you log k. The implication is that when you do the antilog of your intercept, automatically you're going to get your k. So via plotting a graph of log x over m against log y, we can be able to get the constant n and we can be able to get the constant k. And that is what this experiment is all about. So we're going to be guiding you through exactly how you can go about this and how to understand the theory behind this practical and be able to make the most out of it. So looking at this particular experiment, we have some items that have been provided for you in your practical manuals. So in the practical manual, basically what we're working with acetic acid, and the concentration of acetic acid given in the practical manual is 0.5 normal. 0.5 normal acetic acid is what is given in the practical manual. Now, when you get to your laboratory, you could be given the sodium hydroxide is what is going to be used for the dilution process. So we're going to be reading the procedure and then we'll understand much more better. So, but then we are going to be giving concentrated acetic acid, or you don't need to write concentrated, it's not really that concentrated. So your acetic acid, the concentration is 0.5 normal. So, but then in the lab, the sodium hydroxide I will be giving to you is dependent on what the lab attendants decide to provide for you. So, but normally, for this particular experiment, the sodium hydroxide solution that is also given is usually 0.5 normal, usually. So, but then for the purpose of your practical, you may be given something different, and also in your examination, you may be given something different. So, but nevertheless, what you just need to focus on is to understand the theory behind this particular experiment, because when you understand it, you can be able to ace your practicals, you can be able to ace your practical examinations. So, let's read what we have in the manual and understand the procedure, and then we can now go over to the calculations. So, what I have right here is my manual. You can also look into yours and then we'll go together with the procedure. Now, the equipments and reagents, we have the volumetric flask, we have the burette, we have the pipette, funnel, stopper, beakers, filter papers, charcoal, which is the adsorbent. Our charcoal is the adsorbent. And then we have our acetic acid, which is the adsorbate. We then have the sodium hydroxide, which is used for the neutralization, and then we have phenolphthalein, which is our indicator for this particular experiment. What is our indicator for this particular experiment? So, the procedure for this. Now, into each of the stopped flasks, labeled 1 to 5, that's what you have in your manual. So, but then usually what we do in the lab is 1 to 3. So we do with 3 flags instead of 5. But you'll be told exactly what you will do during your time. But for the purpose of this particular video, we are going to be working with 3 flags. If you understand the 3 flags, you can progress to 5. And then you place 2 grams of charcoal. For the purpose of this particular video, we'll be working with 1 gram of charcoal. And then into each of the flags, we place 50 ml of acetic acid solution. So, but then we have 3 flags in this case, as opposed to the 5 flags you have in your practical manual. So the first flask of acetic acid, the flask 1 of acetic acid, contains an acetic acid with a concentration of 0.5 normal. Then flask 2 contains acetic acid with concentration of 0.4 normal, and then flask 3 contains acetic acid with a concentration of 0.3 normal. Now, in your practical manual, they already told you exactly how you can prepare 0.4 normal from the stock solution, which is 0.5 normal, and how you can prepare 0.3 normal from the stock solution, which is 0.5 normal. So you can look at that there, and then I'll be showing you how exactly it was calculated and how you can be able to calculate it and present your work, so that anybody that is looking at your booklet will know that the person who did this work is very much knowledgeable in the practical theory of this, the theory of this particular practical. So the first thing you have to do is to shake each flask vigorously at room temperature. You have your charcoal and you have all of these solutions into the 3 different flasks. So you shake them vigorously at room temperature, and then you allow it to stand for about 5 minutes. What's happening while it's standing? The acetic acid is absorbing to the surface of the charcoal. Then you filter the solutions to separate the charcoal that has some acetic acid absorbed and then the remaining part of the acetic acid that is in the solution. So that's how we did the filtration. Then you collect the filtrate while discarding the first 5 ml of filtrate. Why exactly are we discarding the first 5 ml of filtrate? It's because the filter paper is also going to absorb some amount of acetic acid from the acetic acid that have not been absorbed by the charcoal. So in order to avoid having error while doing your calculations or while progressing with your experiment, you have to discard the first 5 ml because the filter paper must have been saturated with acetic acid. So the other mils that follow afterwards, it will no longer be able to absorb it because it has absorbed sufficient quantity. That's exactly why you have to discard the first 5 ml to ensure that your acetic acid that has been absorbed by the filter paper will not interfere with your results. So the first 5 ml that you have limited acetic acid, you discard it, and then the other mils that begin to follow, you know that the acetic acid content there is in order because the filter paper will no longer be able to absorb more acetic acid while the filtration process continues. Now the manual says analyze the resulting filtrate. Analyze the resulting filtrate by titrating 10 ml of the filtrate with sodium hydroxide solution. We've talked about the sodium hydroxide solution, and in the lab you'll be told the concentration you are given. But for the purpose of this particular practical, we're using a concentration of 0.5 normal. So, and then we're using phenolphthalein indicator of 5 to 10 drops. You can use 5 drops, you can use 6 drops, you can use 7 drops, you can use 8, 9, or 10 drops. So, but the important thing you have to note here is the color change. Now, phenolphthalein is already in the acetic acid solution. That's the filtrate you have is acetic acid. Phenolphthalein in acid is actually colorless, but at the end point, you have it as pink. So the implication is that while you are titrating, you are watching out for color change from colorless to pink. So the color change of phenolphthalein in this context is colorless to pink. So that's exactly what the experiment is. And the moment you are done with your experiment, you begin to fill the tables of reading that you have right there. And in this particular tutorial video, if you look down, you are going to be seeing a link to a document that contains the explanations which I'm going to be giving for this particular video. So you can do well to click on that particular link and also follow along with the explanations that are there in that particular material. So I'll be explaining the material to you very vividly, but when you have the copy yourself, you can always refer back to it and make progress in your academic journey. So let me show you exactly how they were able to get these concentrations 0.4, 0.3 from the stock solution. Now, the way they were able to do that is by using the normal dilution formula. By using the normal dilution formula. Now, the normal dilution formula simply goes this way, that C1V1 is equal to C2V2. That's concentration 1 times volume 1 is equal to concentration 2 times volume 2. So we are going to be seeing how exactly we can be able to work with 0.5, dilute it to 0.4, and also dilute to 0.3 in the lab. So let us start with the first flask. The first flask is already a stock solution, so you are not diluting this. So automatically, you are just having the straight up 50 ml of this in your flask. So, but for this guy, how do we prepare it? Now, we know that our original stock solution which is the concentration of the C1 is 0.5 normal. And then we actually do not know what volume of the C1 we are going to be diluting for us to get 0.4 normal. But we are aware that for each of these flags, everything must be equal to 50 mil. Everything must be equal to 50 mil. So the V1, we do not know about the V1. What about the C2? We know that our end concentration, the concentration we are looking for, is 0.4 normal. This is the concentration we need. And we are aware that the final volume, V2, is going to be 50 mil. So what we're going to be looking for now is the volume of the stock solution that must be diluted for us to get this particular concentration, which is our V1. So we're going to be making V1 a subject of formula. So V1 is equal to C2 V2 divided by C1. So let's do the calculation. C1 is equal to, C2 is 0.4, then our V2 is 50, and then our C1 is 0.5. So if you press this in your calculator, you are going to be seeing that the volume you actually needed for this is going to be 40 mil. The volume you are going to be needing for that is going to be 40 mil. So it simply means that 40 mil of what you have in flask 1, that's the stock solution of acetic acid, 0.5 normal. When you dilute it to 50 mil by adding extra 10 mil of water, the concentration you are going to be having is 0.4 normal. Now, there are two ways you can go about showing this. You can either show the persons that are marking your booklet how exactly you know what to dilute for you to be able to get the concentration, or you can show them how this concentration is gotten from the amount you are diluting. Now, I'm showing you the alternate parts in this particular video. For you to see the other part I talk about, just go down to the link that I'm going to attach to this particular video and download the document that contains these details. You'll see the other part of this particular explanation. So I'm going to be working this part. You see the other part there. Any of them you choose, you go that way. But the idea behind it is to show to them that you know exactly what you are doing and you know exactly what you are doing in this particular experiment. So 40 mil of the stock solution, it simply means that 40 mil of stock plus 10 mil of water, that's H2O. 40 mil of stock plus 10 mil of water, that's H2O. Then let us look at the flask 3. How exactly can we get for flask 3? Same way. Our V1 for flask 3 is equal to C2 V2 over C1. The only thing that must have changed there is our C2. Our C2 this time around will now be 0.3 normal. So we're going to be having it as 0.3 times 50 because 50 remains our final volume. Everything we are working with, the acetic acid volume must be 50. 0.3 times 50 over our C1 still remains our 0.5 normal. So if you punch this in your calculator, what it's going to give you is 30 mil. What does this 30 mil simply tells you? It simply means that what you need for this particular solution is 30 mil of stock, 30 mil of stock plus 20 mil of water. How did I know that we need 20 mil of water? Because I know that if I already have 30 mil of stock, for me to be able to make it up to 50 mil, I just need to add 20 mil of water. And in that way, I have prepared our 0.3 normal, and in this particular way, I have prepared our 0.4 normal. So now we already have our solution 0.5 normal in flask 1, 0.4 normal flask 2, and 0.3 normal in flask 3. So the next thing now is to now progress with our practical. So in the practical, you already have your charcoal and you already have these things inside your flask, and then you are shaking vigorously, allowed to stand for 5 minutes for adsorption process to take place. Then you filter, discarding the first 5 mil of filtrate. I already told you exactly why you should discard the first 5 mil. And then your filtrate, out of your filtrate, you take 10 mil of your filtrate, and then you carry out a titration with sodium hydroxide, a base, in the presence of phenolphthalein indicator that changes from colorless to pink, colorless in acid and then pink at the end point. So let us look at the theory behind that particular experiment, and then I will be able to draft a table that will guide you in this particular process. So permit me, let me just wipe the board, and then we go further. Meanwhile, don't forget these equations. They are very, very vital in the explanations we are making today. So let me first of all write the equation of reaction between acetic acid and sodium hydroxide. As you already know, acetic acid is the old name for what IUPAC, that's the International Union of Pure and Applied Chemistry, calls ethanoic acid. So acetic acid is the old name for ethanoic acid, and the formula is CH3COOH. So this is our acetic acid. Now, acetic acid reacts with sodium hydroxide. This is an acid-base reaction, and then it is going to yield salt. It's going to yield salt and water. It's going to yield salt and water. So this is acetic acid. This is acetic acid, or you can call it ethanoic acid. This is our sodium hydroxide. Then yielding, you can call this sodium ethanoate or sodium acetate. So since we're working with acetic acid, we can call it sodium acetate, but the IUPAC name is sodium ethanoate. And then this is our water. Now let's check if the components of this particular experiment, this equation, they're actually balanced. So how many carbons do we have here? We have 1, 2 carbon. We have 1, 2 carbon. We have 4 hydrogens here. 1, 2, 4 hydrogen, 5 hydrogen. So let us check the number of hydrogen here. We have 3 plus 2, that's 5. So hydrogens are balanced. Then the oxygen here, we have 1, 2, 3. We have 3 oxygens. And here we also have 1, 2, 3. So the oxygens are also balanced. Then for the sodium, we have 1 sodium here. And here we have 1 sodium here. So the sodium is balanced. And then every other thing, we have checked it and they are balanced. Now this equation happens to be a 1:1 equation, yielding 1:1 product. So the implication is that you need 1 part of acetic acid to react with 1 part of sodium hydroxide to produce 1 part of sodium acetate and then 1 part of water. If we are working with mole, it simply means that we will need 1 mole of sodium acetic acid to react with 1 mole of sodium hydroxide for us to be able to get our product. So for every amount of acetic acid you need just an equivalent amount of sodium hydroxide for complete neutralization. So now let's work with what we have here. We are already aware that our stock solution of acetic acid is 0.5 normal, and our stock solution of sodium hydroxide is 0.5 normal. From this practical in the lab, they could give you another concentration. Now, it simply means that if we are going to be working, for example, with 1 mole of acetic acid, and we're going to be working with 1 mole of sodium hydroxide, we can actually calculate the number of moles of those things we have there and be able to know how exactly they can be able to react and know what amount is going to react with what amount. All right, so now what we have there, we have 0.5 normal acetic acid and then 0.5 normal sodium hydroxide. Now because their normalities are same, it simply means that they have the same molar concentrations, because acetic acid will have just 1 hydrogen, then that's for the acid aspect. Then for the base, we have 1 hydroxy group that is actually reacting. So it simply means that we can be able to react 1 mole. We can also react 1 mole of this guy with 1 mole of this other guy to produce 1 mole of this and 1 mole of the other. That's the water we have there. Now, for us to be more scientific in this, let me just show you a little bit of a calculation. Now, 0.5 normal, I already explained to you that 0.5 normal acetic acid is same thing as 0.5 molar acetic acid. So it simply means that what we have there is 0.5 mole per dm cube acetic acid. Now, if we are working with 1 mole, we know that number of moles is equal to concentration in mole per dm cube times volume in dm cube. So I just want to help you understand what we are driving at. Number of moles is equal to concentration in mole per dm cube times volume in dm cube. For us to convert mole to dm cube, we simply divide by 1000. So number of moles is now equal to, for the acetic acid, we simply do 0.5 mole per dm cube times volume. Now, for the purpose of simplicity, let's assume that what we are reacting is, okay, let me just write it by the side. What we are reacting is 1000 mole of acetic acid with 1000 ml of sodium hydroxide. So for the purpose of simplicity, please. Now let's assume that the volume is 1000 ml of acetic acid. So, and I said that for you to convert ml to dm cube, you simply divide by 1000. So the implication is that we have 0.5 times 1000 over 1000. That's going to give you 0.5 mole. So it means that in every 1000 ml of 0.5 normal acetic acid, the number of moles of acetic acid you have there is 0.5 mole. Let us calculate for the sodium hydroxide. For sodium hydroxide has 0.5 normal. 0.5 normal sodium hydroxide is something as 0.5 molar sodium hydroxide. So 0.5 times, we are still using 1000. 1000 over 1000 is going to give us 0.5 mole of sodium hydroxide. So you can already see for yourself that 0.5 mole of acetic acid automatically is going to be reacting with 0.5 mole of sodium hydroxide by reason of the fact that the reaction is a 1:1 reaction. So wiping out the idea of the constitution, since the constitution are equal, we cannot be able to use volumes to be able to navigate around which should react with which and by what extent, or to what extent it should react. So that now brings me back to the explanation of the practical itself. So follow me very closely because this is a very important time in this particular video. Now, we are told that 10 ml of the filtrate is what should be neutralized by sodium hydroxide. So think with me. If we need 10 ml of acetic acid without adsorption, we need 10 ml of acetic acid without adsorption, and we are aware that the concentrations are same concentrations, and we are also aware that the reaction is a 1:1 reaction. What amount of sodium hydroxide are we going to be needing? You are very correct if you thought about 10 ml also. Since it's a 1:1 reaction, and we have 10 ml of acetic acid without any form of adsorption, then it simply means that we need 10 ml of the same 0.5 normal sodium hydroxide for us to have a complete neutralization. For us to have a complete neutralization, you may want to pause this video and go back and watch this again for you to understand the point I'm trying to make. Now, we are aware that when you shook it with the charcoal and you allow it to stand for 5 minutes, the charcoal is an adsorbent, it absorbs some of the acetic acid. It simply means that the volume that will now be required to neutralize the acetic acid will no longer be equal to 10 ml because the amount of acetic acid has reduced by reason of the adsorption by the charcoal. So the implication is that when you are doing your titration without adsorption, the maximum titer value you should have for sodium hydroxide should be 10 ml. But we are aware that adsorption took place while standing. So the implication is that the titer value you should have should not even be up to 10 ml. Does that make sense? Does that make sense? So we are going to be going over now to the titer value that can be able to work for this particular experiment based on what has been carried out and some necessary analysis that have been done already prior to this time. So we're going to draw our titer table and then we're going to be making progress on this particular part. All right. So here what we have here is the table that is showing our titer value for the different stages of the experiment. So like I mentioned, for the first flask, if we did not have any form of adsorption taking place, we would have needed exactly 10 ml of sodium hydroxide to be able to neutralize 10 ml of the acetic acid, since both of them have a concentration of 0.5 normal. So, but then because some level of adsorption had taken place, we now have a titer value that is less than 10, which is 9.60. We now have a titer value that is less than 10, which is 9.60. So the next flask you have is the flask that contains 0.4 normal acetic acid. So let us do some level of calculation so you can understand that. Now when you want to calculate for the base, acid and base, usually use concentration of acid times volume of acid is equal to concentration of base times volume of base. So what we call that is CAVA equal to CBVB. Now the reason why we are using this is because the reaction is a 1:1 reaction, because the original equation actually is put in this form: CAVA over CBVB, which is equal to NA over NB. So since this is 1:1, automatically you can go to get this here and you're good to go. So since the 1:1 reaction, we will not need to have this in place. We will not need to have this in place. So saying that this is a 1:1 reaction, let us work with the second flask. Now for the second flask, we said that the concentration of the acetic acid there is 0.4 normal, and remember we are still using 10 mil. So let me assume that there's no adsorption. So we're using 0.4, no adsorption times 10 mil. The concentration of our base still remains 0.5. That's our sodium hydroxide. Let me write that again just so I don't forget. Remember our sodium hydroxide, what we're working with is 0.5 normal, and then the stock of acetic acid, the stock is 0.5, flask 1 0.5. Let me just put that here, 0.5 normal, then flask 2 0.4 normal, flask 3 0.3 normal. So we're working with flask 2 now. So 0.4 times 10 is equal to 0.5 times, we don't know the volume of base that is going to be necessary to neutralize this volume of acid when there's no adsorption. So we can make the volume of base subject to formula so that our VB is equal to 0.4 times 10 divided by 0.5. So if you do this calculation appropriately with your calculator, what you should be getting is 8 mil. It simply means that 8 mils of sodium hydroxide in the absence of adsorption, 8 mil of sodium hydroxide in the absence of adsorption is automatically going to be needed to neutralize 10 mil or 0.4 normal acetic acid. But we are very much aware that adsorption took place after shaking and allowing to stand for 5 minutes. The implication is that your titer value is not going to be up to 8 mil. So you have to take note of all of these things when you are carrying out your experiment, because when you understand the theory behind the experiment, you can able to carry out the experiment excellently as you ought to do it. So the implication is that our titer value should not be up to 8 mil. So based on some level of analysis, a very appropriate titer value you want to work with, considering the conditions of the experiment, is 7.7 first titer, 7.6 second titer, 7.65. Like I told you, the document that is attached to this particular video, you're going to find the document that contains all of these details. So let us make progress now for the last flask, flask 3. Flask 3 happens to have a concentration of 0.3 normal acetic acid. So let us replace this now. Let us replace this with 3, and then let us replace this with 3. Now, if we're working with 0.3 normal acetic acid, we want to know what volume of 0.5 normal base is going to be necessary to neutralize 0.3 normal acetic acid, 10 mil, if there is no form of adsorption. So using that formula, what we're going to be getting, if you press your calculator, is going to be 6 mil. It simply means that without any form of adsorption, the volume of base necessary to neutralize 10 mil of 0.3 normal acetic acid is going to be 6 mil. It means that when you're carrying out this practical after adsorption, you should not get any titer value that is greater than 6 mil. It should not even be up to 6 mil, because we are aware that adsorption had taken place already. Hence, via some level of analysis, we've been able to come out with these particular values as appropriate values you can want to use for your titer value. Now, another thing again I want to bring to your knowledge is that concentration of the adsorbate or the adsorbent also affects the level of adsorption. Now, when we talk about concentrations, when we talk about practicals, we have to know which of them is variable and we have to know which of them is fixed. Now, in this particular practical, all through the flask, you are using 1 gram of charcoal. All through the different class, you are using 1 gram of charcoal. So the implication is that the adsorbent has a fixed amount, has a fixed mass. So, but then the adsorbate, which is the acetic acid, do not have a fixed amount. The implication is that you are having acetic acid 0.5 normal, acetic acid 0.4 normal, acetic acid 0.3 normal. So let us now work with the one that is variable, and let me explain a few things. Now, in the first flask where you have 0.5 normal acetic acid, you have a higher concentration of acetic acid. The implication is that the absorption, the amount of absorption that will take place there will be higher than the amount of adsorption that will take place in 0.4 normal, because the concentration had gone down. And then will also be much more higher than the level of adsorption that takes place in the 0.3 normal, because the more concentrated or the more available, the more concentrated the adsorbate, the more the adsorption that takes place in that particular regard. So same thing for the flask 2 and same thing for the flask 3. So with that in mind, you can now be able to see the trend in the values we are having here. For example, if you look at this particular value, this is 9.60. That is about 0.4 mil lost in reaction with the in terms of the amount of adsorption that took place. Let me explain that quickly. Now, we said that 10 mil of base is going to be needed to neutralize 10 mil of 0.5 normal acetic acid in the absence of adsorption. But when adsorption took place, we are now having an average titer value of 9.60. It simply means that about 0.4 mil in terms of volume, about 0.4 mil of acetic acid had already been absorbed by the charcoal. So it means that what we have left is 9.6 mil, and automatically you just need 9.6 mil of base to neutralize it. I mean in terms of volume. Now if you come down to the second one, 0.49, what we have is 7.65. It simply means that the amount of acetic acid that has been absorbed in this flask is 0.35. Here is 0.4 mil, here is 0.35 mil. You already see that the amount of acetic acid that has been absorbed is reducing because the concentration of the adsorbate is also reducing. If you look at this 5.75, that's what we have here as what has been absorbed is 0.25. The more the concentration of the adsorbate, the more the amount absorbed. But the lesser the concentration of the adsorbate, the lesser the amount absorbed. So that's what this particular trend will help you understand. So now let us go further and begin to calculate what is necessary for us to fill up the table that you have in your practical manual, so that we can be able to have a very good flow. I will need to do the calculation for the new concentration of that particular solution where adsorption has taken place. The moment I do that calculation, then I will draw the table very clearly for you to see it, and then we'll begin to fill the parameters in the table, and then I will guide you through on how you can go about your graph and do very well in your practical examination. So let us walk over through the calculation that we are needing for us to get the concentration, the new concentration of the acetic acid you have. Now, the reason why we're calculating this concentration is because in that table, you will need to fill in the concentration. Like I mentioned, just look into your practical man and look at the table. You will see where we're talking about the concentration after adsorption, the concentration of acetic acid after adsorption. So, but then I'm going to be drawing the table again for you, and I'm going to be explaining that. But for now, let us just first of all do our solving. So we are still going to be using the formula CAVA equal to CBVB. Now, what is our CA? That's the concentration of the acid, the acetic acid. What's our VA? The volume of the acetic acid. Now, in this case, we are using 10 mil because the filtrate we are taking out of the filtrate are just measuring 10 mil of the acid. So our VA continues to be 10 mil. Then our CB is the concentration of the base that is used. And in this case, we are using 0.5 normal sodium hydroxide. Then the volume of base is now going to be our Titer value. That's the volume of sodium hydroxide that is being used to neutralize the acetic acid you have after adsorption. So it means that what we are now looking for here is just the CA, because we don't know the concentration of the acetic acid after adsorption. Before adsorption, the first flask contains 0.5 normal, the second flask contains 0.4 normal, and the third flask contains 0.3 normal. But after adsorption, all of these concentrations are going to be reduced because the charcoal had been able to get some amount of the acetic acid adsorbed on its surface. So let us start with the first flask. So for flask 1, CA is equal to CBVB over VA. So our CB, concentration of base, is 0.5, and then our volume of base is our Titer value, and the average Titer value is 9.6, and then our volume of acid, which is 10 mil of the filtrate, is 10. Now, if you put this in your calculator, what you're going to be getting as your value for the concentration of the acid in the first flask is going to be 0.48 normal. 0.48 normal. So it simply means that after adsorption in 5 minutes, the concentration in flask 1 has reduced from 0.5 normal to 0.48 normal. So let us calculate for the second flask. Let's call this flask 1, and then let's call the next one flask 2. Now in flask 2, our CA is still equal to CBVB over VA. And then our concentration of base is still 0.5. Our Titer value for flask 2 is, average Titer value is 7.65. How do you calculate average Titer value? You simply add the two of them and you divide by 2. Yeah, if you have 3, you add 3 and divide by 3. So 0.5 times 7.65 divided by, what's the volume of our acid? That's the volume of the filtrate we are using, which is 10 mil. So that's going to give you 0.5 times 7.65 over 10. That is automatically going to be giving you 0.3825 normal. So the concentration of the acid in flask 2 has reduced from 0.4 normal to 0.3825 normal because of adsorption by the charcoal that is present there. So let us look at the calculation for flask 3. Flask 3, we have Ca equal to Cb Vb over Va. We have Ca equal to Cb Vb over Va. So what we are going to be having, Cb is still 0.5, and our Vb is our Titer value, which is 5.75, our average Titer value. And then our Va is going to still remain 10 because we're using 10 mil of the filtrate, which is for the acetic acid. Now, if you punch that into your calculator, what you're going to be having as your result is going to be 0.2875 normal. 0.2875 normal. So the moment you have been able to get this, you have been able to get the concentration of the acid that is currently present in the different flasks after adsorption. Are we making progress now? So now I'm going to be drawing the table that is going to be necessary for you to be able to carry out your final plotting of your graph and then estimating for the value of your K and your N. So let us make progress. So this is our table right here. I've been able to draw the table out, and like I mentioned, the document attached to this video, you'll find the table and every other detail you need for this practical to go seamlessly for you. So now in the table, what we have here is first of all flask. Flask 1, 2, 3. The weight of charcoal we use, we already mentioned from the start, is constant, and for this particular practical, we are taking it as 1 gram. Now, one thing you must note is that when you are drawing tables, you must ensure you write the constituents of the table very well and also write the units. So this is weight of charcoal used, and from the start, we mentioned that to represent the weight of the adsorbent, what we use is M, and the unit is gram. So what we have is 1 gram, 1 gram, 1 gram. Now, the concentration of acid before adsorption is referred to as CO, and the unit is normal, N in brackets. So it's very important to take note of those things when you are working with this particular experiment in the lab. So the first flask contains 0.5 normal, second flask contains 0.4 normal, and the last one contains 0.3 normal. Now, you must have already noticed that the number of decimal places we are using, they are consistent. So we're going to make this 4. You can leave it as 3. As 3 decimal places, they are also very fine. So, but for consistency purpose, we are using 4 decimal places across the table. So we have 0.4, 0.5, 0.4, 0.3. But then after adsorption, that was the calculation we did at this side of the whiteboard just some minutes ago. So the first one, the concentration after adsorption, which is CE normal, is 0.48. After adsorption, for the second flask is 0.385, and for the last flask is 0.2875, based on the calculation we have done prior to this particular time. So the next thing we want to calculate is the adsorbed quantity, which we call K. And the adsorbed quantity is simply concentration before adsorption minus the concentration after adsorption. So I know the amount of the acetic acid that had been absorbed by the adsorbent, which in this case is our charcoal. So when we do that, 0.5 minus 0.48 with your calculator is going to give you 0.02. And then you also do that for this minus this, we give you that. This minus this, we give you that. Then the next thing you want to calculate is your X over M. Your X over M. Your X, sorry, I made a mistake. This is not K. This is X, sorry. This is not K. K is actually our constant. This is X. So your X, which is the adsorbed quantity, over your M, which is the weight of charcoal, is going to give you this. Now, since the weight of charcoal all through is 1 gram, 1 gram, 1 gram, it simply means anything divided by 1 will give you the same thing. So what you have here is 0.02 divided by 1 will still give you 0.02. 0.0175 divided by 1 will still give you 0.0175. Same thing for the last one. So that is that about this. Then the next thing you want to do is your log X over M. What you simply do is to do the logarithm of this, and then you get these particular values. Now, where students usually get confused is, what is now your log Y? What is the Y? That is the question many people ask. What is the Y? And I'm here to answer that question for you. Your Y is simply your concentration of acid after adsorption. Your Y is the concentration of the acid after adsorption. So you can take note of that. Your Y is equal to CE. What is CE? CE is the concentration of the acid after adsorption. So that is that about that. So we have been able to get our log X over M and then our log Y. In your practical booklet, you will be informed that you should plot a graph of log X over M, a graph of log X over M against log Y. So it simply means that log X over M will be on the X axis, will be on the Y axis, and then your log Y will be on the X axis. Now many students get it mixed up. Because we have log X over M, they want to put log X over M on the X axis. And then because we have log Y, they want to put log Y on the Y axis. Automatically, you are going to be making mistakes in getting your N and also your K. So, but for accuracy purpose, you want to master it now while this video is still ongoing. Then log X over M is going to be on your Y axis, while your log Y is going to be on your X axis, because it's a graph of log X over M against log Y. So what we have here is a graph that shows you what your graph is going to look like. Now, for your own good, I will recommend that you go ahead and plot your own graph. The reason I don't want to go ahead to plot any graph in this particular video is to avoid people having same graphs across their practicals. So, but for mastery purpose, you want to go and plot your graph, and I will tell you exactly the indices you have to check to know if the graph you plotted is in order. Meanwhile, for your notice, your graph will look something like this. That's why I had to draw this particular sketch here. Now, in this particular graph, we have our X over M on the Y axis, and we have log Y on our X axis. Now, on a graph sheet, these parts are, this is positive Y, this is positive X. Meanwhile, this is negative X, and this is negative Y. If you look at the values we have here, all of them are negatives. The simplification is that your graph will be captured within the regions of the negatives. That's negative X and negative Y. So when you want to plot your graph, you have to take note of how to be able to do this. So let us use the first two values to understand how those points can be gotten. Now, this is log X over M. The first point is minus 1.69, and the second point is minus 1.75. If you are going to be reading that on your graph, you are going to be going this way, because this will be like your 1, 2, 3, 4. So it means that your 1.69 will come first before your 1.75. and then before your 1.9. So the counting will be going this way. Now, same thing for your log Y. Sorry, I interchanged it now. The log X over M, is on this particular part. If you're going to be counting, your 1, 2, 3 will go this way. So you have log 1 minus 1.69 first before minus 1.75, then before minus 1.9. Then for your log Y, you will have log minus 0.3 before your log minus 0.4, before your log minus 0.5. It is very important to choose a scale that will work for you. But make sure you have practiced before you enter the examination hall, so you don't get disarrayed by reason of the kind of question you have, and by reason of the fact that you don't have so much time to complete the practical. So when you have been able to plot the points together, you have a positive graph which is on the negative region, and then you draw your triangle, and then you get your slope. So this is going to be your Y2, this is going to be your Y1, this is going to be your S2, and this is going to be your S1. Now, let us come back to our equation, our friendly equation that have been modified by use of logarithm. Log X over M equal to N log Y plus log K. And we say that this is also equal to the equation, or relatable with the equation of a straight line, which is Y equal to MX plus C. You can already see from the graph that actually what we have there is a straight line. When you are plotting your graph, make sure you have your title of your graph, make sure you have the scale of your graph, make sure you have your date on your graph, make sure if you are writing an examination, you must have your reg number also written on your graph. And then you must ensure that you label your graphs appropriately. The axes, you label them appropriately. You also ensure that you indicate your Y2, Y1, S2, S1, and also make sure your triangle is as visible as possible. And ensure that the pencil you are using to draw your line is not so thick, so that the line can be very, very sharp and precise in passing through the points. What you have here are just 3 points. The implication is that when you are drawing your graph should be such that at least 2 points should pass, like the line should cut across 2 points, at least 2 points. If you can get it to cut across 3 points, that's fine, but it should pass at least 2 points for this kind of graph for you to get a very nice result. Now, when we now relate this particular equation with that of the equation of a straight line, I mentioned that y simply means what's on the y-axis, and like you can already see already, log x over m is on the y-axis. And I said x simply means what's on the x-axis, and like you see already, log y is on the x-axis. So the n is same thing as the m, and m in a straight line simply means slope. So our slope is equal to m, which is also equal to our n, and that is given by y2, that's changing y over changing s, that's y2 minus y1 over s2 minus s1, like you have gotten from your graph already. When you get your value, make sure that your n is in between 0 and 1. Make sure that your n is in between 0 and 1. So the value you get for your n should be somewhere between 0 and 1. It should not be less than 0, and it should not be greater than 1. So you can test it out from your own graph and see what works for you, and ensure that you're able to carry that through even in your life examination. Now, the next thing you want to check for is for your k, because according to the question, you should be looking for your n and for your k. Now, c simply means intercept on the y-axis. So this is our intercept on the y-axis. So we go there and we read this particular point on the y-axis, and that becomes our c, our intercept, and that is equal to log k. What we are looking for in this practical is not log k. What we are looking for is k. So what we simply need to do is to do the anti-log of c for us to get our k. So the moment you do the anti-log of your intercept, automatically you get your k. Then you now write out your conclusion for the particular practical, and then you begin to list out the precautions you took while ensuring that your graph has the appropriate details that ought to be present there. So with that, we have been able to complete the adsorption experiment. If there are changes in the concentrations of the things you are using, same formulas, same theories I've explained earlier on is what you can use to be able to navigate through such challenges. And if you have further questions, you may want to reach out to us via whatever contact details you are going to see in there, or ask your questions in the comment section, and it will be attended to as soon as possible, so that your academic journey will be less hectic for you. So that is that about the adsorption experiment. So go ahead and ensure that you draw your graph, practice these things. If you have questions, ask in the comment section or reach out to us via any of the contact details you have there in this particular video. And with that, we are very good to go. Thank you so much, and wish you success in school.